Good morning, dear students, and once again, welcome back to our course. In the last lecture, we are solving numerical on how to draw the root locus for a given system. And once you have a knowledge of how to draw root locus for a system, how to identify the stability of that particular system. So, we solved some 2 to 3 numericals on what exactly root locus technique is. And one thing I would like to tell you that root locus is a graphical technique through which we are trying to identify the stability of a system when we vary the gain k from 0 to plus infinity. And in that particular range, suppose if you are interested to calculate that how the location of poles of open loop transfer functions are going to vary, that we can easily identify through this particular technique. And we are solving some numerical on that, and I think this is what the numerical which we are trying to solve in the last lecture, where our objective is to draw the root locus for this particular open loop transfer function, having the open loop transfer function gain g of s into h of s equals to k divided by s plus 6 s square plus 4s plus 13. And apart from drawing the root locus for this particular system, we are also in a position to determine number one, breakaway point, number two, angle of departure, and number three, we need to make a comment on system stability. So I think we have completed about the first portion. What is the breakaway point in this particular case, and what will the range of k for which the system is stable, unstable, or marginally stable. The thing is that we are trying to identify that how to calculate angle of departure for this particular case. So first we will see and discuss how to calculate angle of departure for this particular system. And once we have done with this, then we will start one of the most important topic, and that will be the last portion as far as control system course is concerned, and that deals with the concept of Bode plot. What exactly Bode plot is, and how we can draw Bode plot for a given system. What is the importance of Bode plot? What kind of informations we can collect once we know the Bode plot for a system? The entire things we are going to discuss in the coming sessions. So, as far as the root locus for this particular system is concerned, first of all, we need to obtain the open loop transfer function for a system which is directly given to us. Then we need to obtain how many number of poles and zeros are available in this particular system. So here we have 4 poles, and let us try to calculate them at which location the poles are available. So one pole is available at origin, another one is available at -6. Then we have a pair of complex conjugate pole. One pole is available at -2 plus 3j, and another one is available at -2 minus 3j. And then we need to decide how many number of branches will be there for this particular root locus. So if you apply a proper logic, we know that number of branches available in root locus is always going to be equals to either p, or it will be like 0. When it is going to be p, when p is more than z, and when it is going to be z, when z is more than p. So this simple logic we need to implement in order to decide how many number of branches are available in this particular root locus of the system. So finally we conclude that here number of branches are nothing but p, which is going to be equal to 4. And we also need to find out what will be the section of root locus that is going to be lie on the real axis, and the answer for this is in between 0 to -6. Again, you need to apply the same topology, that you have to consider a reference point and then calculate how many number of poles and zeros are available on right hand side with respect to that reference point. If the summation is odd, then we can say that root locus is going to lie, and if the summation is even, then root locus does not exist in that particular location. That is important. Then we need to decide what will be the nature of branches. So in this particular case, because we have a 4 pole like this, and no zeros. And I told you that the moment we put k equals to 0, poles are more dominating in nature. That means by default, all the branches are going to start their journey from open loop pole, and they are trying to move towards the open loop 0. But in this case, because we don't have any zero, so by default, we are going to assume that their zeros are going to available at infinity. So all the branches will start their journey from open loop pole, and they are going to try to move towards the infinity like this, like this. So here we have one more infinity, and then here we have one more infinity like this. So the moment we conclude that in this case all the four branches will start their journey from open loop pole, and they are going to terminate towards the infinity, definitely we need to think that we need to provide four different directions for each branch, so that they can start their journey from open loop pole and move towards the infinity. So hence in this case, the angle of asymptote and the asymptotic line that we need to draw are 4, because in this case p minus z is nothing but 4 minus 0, which is nothing but 4. And if you apply this formula, we can easily calculate the value of angle of asymptote for each value of k. The value of k vary from 0, 1 to up to p minus z minus 1. So p minus z is 4, 4 minus 1 is nothing but 3. So k is going to take the value like 0, 1, 2, and 3. So what we need to do, we need to put k equals to 0 and calculate the value of theta. Then put k equals to 1, calculate the value of theta. So if you apply that logic, you will get k as 45, 135, 225, and 315 respectively. And then we need to calculate the reference point where we need to draw all these angle of asymptotes. And the reference point is called as centroid. This is very important. And the formula to calculate centroid is summation real part pole minus summation real part of 0 divided by p minus z. So if you apply that logic, we came to know that the centroid for this particular case is minus 2.5. And then calculate the breakaway point. As I told you that in order to calculate a breakaway point for any system, first of all we need to obtain the characteristic equation for that system. And the characteristic equation is like this. So this equation indicates the characteristic equation. Then we need to arrange this equation in terms of k, then take dk by ds, equate that particular term to 0. You will get this equation as an output, and then apply factorization technique to calculate the valid breakaway point. And finally, if you apply that logic, s equals to minus 4.2 is going to be a valid breakaway point. Why? Because if you put s equals to minus 4.2 in this equation, you will get k as positive. So the range of k for which the system is stable, unstable, or marginally stable, that we can obtain by applying the concept of Routh array, or you can say Routh-Hurwitz criteria. So for that, first we need to arrange the characteristic equation in the standard form, and then construct Routh array, and then we need to apply the technique of Routh-Hurwitz criteria for which the system is stable, unstable, or marginally stable. So according to Routh-Hurwitz criteria, a system is said to be stable if all the elements in first column of Routh array have got the same sign. So this is plus, this is plus, this is plus. For system to be stable, this must be greater than 0, and this also must be greater than 0. So if you apply that logic, we will get this as an answer. So this is what the range of k for which the system is going to be stable. That means from 0 to 229.4. This is very important. And the moment you put k equals to 229.4, the system is now going to be under the category of marginary stability. Why? Because it will be the special case for Routh-Hurwitz criteria. The moment you put k equals to 229.4, this entire term is going to be what? 0. So if you consider that this will be the fourth row of route array, all elements of fourth row of route array is going to be 0 if you put k equals to 229.4. So this will be a special case, and to avoid this we need to apply the concept of auxiliary equation. So this is going to be the auxiliary equation for this particular case. So I can write here as auxiliary equation is going to be like 29.2 into a square plus k, and this is going to be auxiliary equation if you put k equals to 29.4. This is going to be 0. That is important. So if you apply that logic, we can find out the value of s corresponding to the marginary stability of the system. That means at this particular values of s, the root locus of this particular system is going to cut the imaginary axis, and the value of k corresponding to this is going to be 229.4. This is very important. So if you refer the statement of the numerical, here our objective is to calculate the value of breakaway point, and we came to know that the valid breakaway point is minus 4.2, and then we need to make a comment on system stability. So finally we have this range. That means if the value 229.4, this is point. So finally we conclude that if the value of k is in between 0 to 229.4, the system is said to be stable. At k equals to 229.4, the system is said to be marginally stable, and the moment you increase the value of k above 229.4, the system is said to be unstable. This is very important. Now the only one portion that is remaining over here is nothing but calculation for angle of departure. How to calculate angle of departure? That portion is remaining, and in the last lecture we have stopped at this particular point. Calculations for angle of departure. So first of all, we need to think that whether we need to do this calculation or not, and the answer for this is yes. Why? Because I told you that angle of departure and angle of arrival, these are the two concepts that we need to implement whenever we are dealing with complex conjugate pole and complex conjugate zeros. Why? Because complex conjugate pole is a pair of pole where or from where the branches are going to start their journey as far as root locus is concerned. So definitely we need to provide a direction through which branches are going to leave and start their journey. So that direction is provided through angle of departure. In the same way, whenever we are having a concept of complex conjugate zeros, so at zeros all the branches are going to terminate. So the moment we can say that the branches are going to terminate at zeros, so definitely we need to provide a direction through which branches are going to arrive at the complex conjugate zeros. So that directions we are going to provide through angle of arrival. So this is very important. So in this case we have a pair of complex conjugate pole. I think one pole is available at -2 plus 3j, and another one is available at -2 minus of 3j. So in this case we have a pair of complex conjugate pole. Hence we need to find the concept of angle of departure. That is important. So take your pen paper and try to calculate the angle of departure, because so far whatever the numericals that we have discussed on this topic, they don't consider the concept of calculating the angle of departure or angle of arrival. So this is the first numerical where we are trying to calculate angle of departure. But we discussed in detail in theoretical aspect that what exactly angle of departure is and how we can calculate that. So what we need to do is, first of all, we need to create a structure where we have to draw all possible poles and zeros corresponding to the system. So with respect to the open loop transfer function of a system, here we have four number of pole, out of which one pole is available at 0, another one is available at -6, another one is available at -2 plus 3j, and another one is available at -2 minus of 3j. See, all these poles we have indicated on our pole 0 plot. So one pole is available over here, another one is available over here, then one pole is available over here, and finally this is the another pair of complex conjugate pole. Now what we need to do, the mathematical formula to calculate angle of departure is nothing but 180 minus summation of ip minus summation of iz. So based on that, first of all we need to calculate summation of ip followed by summation of iz, because in this particular case we don't have the concept of zero, so summation of iz is going to be almost zero, but we need to calculate the value of what, summation of ip. So what we need to do is, first of all we need to indicate the poles in the S plane, and then based on the complex conjugate pole, it may be -2 plus 3j, or it may be -2 minus of 3j. Out of these two, uh, we have to consider that any one of them as a reference pole. Suppose I need to consider that this is going to be a reference pole. So what we need to do, with respect to reference pole, we need to connect all the remaining poles by a dotted line. So this is your reference pole. So let us consider that we need to connect this with respect to the pole available at origin, then connect this with respect to pole available at -2 minus 3j, and then available at -6 by dotted line. And then we need to calculate the angle subtended by this particular pole with respect to the reference pole. For example, this 5p1 is nothing but the angle subtended by the pole available at origin with respect to the reference pole. In the same way, 5p3 indicate the pole subtended by -2 minus 3j with respect to the reference pole. In the same way, 5p2 is nothing but the angle made by the pole available at s equals to -6 with respect to the reference pole. And remember one thing, that whenever we are trying to calculate the angle in the anti-clockwise, all the angles are going to be what, positive. See, this is going to be anti-clockwise, so positive. This is going to be anti-clockwise, hence positive. So if you apply this logic, let us try to calculate the value of ip1. So ip1 will be 90 plus this particular angle. In the same way, this is going to be another angle, and this is going to be exactly 90 degree, 5p3. So if you try to calculate the value of 5p2, it will be like tan inverse of opposite by base. So I can write here as 5p2 is going to be like tan inverse of opposite. So this is nothing but a triangle, opposite is nothing but 3 divided by base. So here the base is going to be 4, because this is 6, this is 2. We need to calculate only the magnitude, so it will be like 4. So this is what the value for 5p2. In the same way, suppose if you're interested to calculate 5p3, so I am can 5p1, sorry. So 5p1 is going to be like 90 plus this particular angle, and this angle can be calculated by taking this as a triangle. This is going to be opposite, so it will be like tan inverse of opposite. Opposite is nothing but 2 divided by base, so base is nothing but 3. See, this is going to be the base is nothing but 3, opposite this is going to be your 2. That's it. So if you apply that logic, we can calculate the value of 5p1, 5p2 and 5p3. See, so finally 5p1 is going to be 123.6, 5p2 is 36.86, and 5p3 is nothing but 90. Then calculate the angle of departure. Mathematical formula is 180 minus 5p minus 5z. So 5p is the effective angle of 5p1, 5p2 and 5p3. So if you apply that logic, 5p is 250.46, and from equation number 1 we can calculate the value of angle of departure, and the angle of departure for this case is -70.46. This is very important. So With respect to this particular pole, we calculate the angle of departure and the value is minus 70.46. Minus means we need to indicate this particular pole, or with uh, respect to the reference pole, we need to draw this particular angle in the clockwise sense. As I told you that in anti-clockwise we need to take the angle as positive. Here in this case angle is negative, hence we need to indicate them in clockwise sense. So first of all we need to draw a reference axis which will be parallel to your x-axis, and then we need to indicate this minus 70.46 degree angle. So minus means we need to indicate them in clockwise. So with respect to this reference axis, here we need to indicate this angle. This angle is going to be your minus 70.46 degree. I hope this point is clear to everyone. So the moment we came to know that the angle of departure for this particular pole is minus 70.46, suppose if you take this pole as a reference pole, then in that case if you apply the same logic you will get the value of angle of departure as plus 70.46 degree, and plus means it will be in anti-clockwise sense. So the angle will be like this, it will be in the anti-clockwise sense, and the answer will be 70.46 degree. So this is very important. So it depends upon what kind of complex conjugate pole we have taken as a reference, and based on that we need to calculate the value of phi d. It may possible that phi d may be positive, may be negative. The thing is that if phi d is positive, that means we need to indicate them in anti-clockwise. If phi d is negative, we need to indicate them in clockwise. This is very important. So based on this, this is what the final structure for the root locus for this particular system. Now see here, see, this is nothing but the pole, this pole where we indicate the angle of departure. It is minus 70.4, that's why we have indicated them in the clockwise direction. So this is what the angle of your minus 70.4. In the same way here it will be like plus 70.4 in the clockwise sense. I hope this point is clear to everyone. And then we need to indicate the nature of root locus for this particular system. So see here, the moment you put k equals to 0, basically you are at pole. See, one pole is available at origin. So the moment you put k equals to 0, so one branch will start from s equals to 0, and another one is start from s equals to minus 6. In the same way, one branch will start from this particular pole minus 2 plus 3j, and another one will start from minus 2 minus 3j, and then they will start their journey like this. So here let us focus and follow this arrow indicated by yellow color. So here one pole is at 0, another one is at minus 6, so one branch will start from minus 6, another one will start from 0, and they will reach at breakaway point. So here this is the breakaway point, this is called as the breakaway point. This is nothing but your breakaway point, breakaway point, and then one branch is available and move towards infinity along the angle of asymptotes of minus 135 degree. Another one is available at infinity along the angle of asymptotes towards 45 degree, like this. And then see, another pole is available at minus 2 plus 3j. So one branch will available from this particular point, and then it will move like this towards infinity along the asymptotic angle pole of 45 degree. This is for 225 and this is for 45. And then another branch will available, and it will start its journey from minus 2 minus 3j, and it will move towards this. And this is nothing but a point where the system is going to marginally stable, and the value of s corresponding to this is nothing but plus minus 2.98 j. This is very important, and the value of k corresponding to this is nothing but 229.4 or 229.4. That means the moment, if you vary the value of gain k from 0 to 229.4, the system is said to be stable. Why? Because the location of poles with respect to imaginary axis are on left hand side of the imaginary axis. The moment you put k equals to 229.4, the system is said to be marginally stable. That means you are at this particular point followed by this particular point. And the moment you increase the value of gain k from 229.4 onwards, see, the location of poles are on right hand side with respect to imaginary axis, and the system is said to be unstable. This is very important. So take your time, try to draw. Let me erase this so that you can draw the exact figure for this. So this is what the final answer of our question. Our objective is to draw the root locus for the system, and this is what the final answer is. And here we came to know that how to find the angle of departure for the system, followed by what will be the range of k for which the system is stable, unstable, and marginally stable. So please draw this. This is very important, and this will be the end of root locus technique. So as far as gate is concerned, as I told you that no one is going to ask you to draw root locus for a system, but whatever the steps that we have learned in the last lectures, through which we can draw the root locus for a given system, based on those intermediate stages, you may have various types of numerical on gate. For example, someone may ask you that what will be the nature of branches that are available in the root locus, or someone may ask you that calculate the angle of departure, calculate the centroid, what will be the range of k for which the system is stable, unstable, marginally stable. Or it may possible that someone may ask you to calculate angle of departure if we have the pair of complex conjugate pole. Or it may possible that someone may ask you to calculate angle of arrival as far as we are dealing with the concept of complex conjugate zeros. So you should know how to draw all these steps in detail. Okay, so if you are done with this, now let us try to start one of the most important topic, and this will be the last topic from my side on control system that deals with the concept of Bode plot. So what is Bode plot? What is the importance of Bode plot? And how to draw Bode plot for a system? How we can identify the stability of system using Bode plot, that we are going to learn in detail in this particular lecture. So first of all, let us try to understand that what exactly Bode plot is and how we can define the stability of system using Bode plot. So first of all, Bode plot is nothing but a graphical technique through which we are trying to identify the stability of a system in the frequency domain. This is very important. So it is nothing but a technique through which we are trying to identify the stability of a system in frequency domain via graphical technique. And whenever we are trying to find out, or we are trying to draw the Bode plot for a given system, ultimately we need to draw two plots simultaneously. First plot is called as magnitude plot, and another one is called as phase angle plot. So when I say that we are trying to draw the Bode plot for a system, ultimately we need to draw two plots simultaneously. First one is called as magnitude plot, second one is called as phase angle plot. That is important. Now what is magnitude plot? So the magnitude plot of a system is nothing but a kind of plot where we are trying to draw the magnitude of an open loop transfer function in decibel with respect to the frequency on the logarithmic scale. This is very important. So what is magnitude plot? In magnitude plot, we need to draw a plot where on the y-axis we are going to take magnitude of open loop transfer function, which will be like magnitude of gj omega followed by hj omega, and on x-axis we need to take frequency, which will be in logarithmic scale. That is very important. So whatever the plot which we are getting as an output, that indicate the magnitude plot for the system. This is very important. And remember one thing, that whatever the magnitude that we are going to draw, that has to be in decibel. That means we need to take 20 log to the base 10 of your magnitude of open loop transfer function. That is magnitude of g j omega h j omega. Because we want to calculate the magnitude in decibel. This is very important. In the same way, what is frequency plot? So frequency plot is nothing but the variation of phase angle of an open loop transfer function, which is nothing but angle of g j omega h j omega, which will be in degree, which is very important, with respect to the frequency that will be on the logarithmic scale. So this is the plot where we are trying to draw the phase angle contribution, or you can say the angle of open loop transfer function, which will be in degree. So here we need to take angle of your gj omega followed by hj omega. This will be in degree with respect to frequency, which will be in the logarithmic scale. That is important. So whatever the graph which we are getting as an output, this will be your phase angle plot. That is important. So ultimately, to draw Bode plot, we need to draw two plots simultaneously. First one is called as magnitude plot. Second one is called as phase angle plot. That is important. In magnitude plot, we are going to take the magnitude of open loop transfer function, which will be like mod of g j omega into h j omega, which will be in decibel with respect to the frequency. That will be in logarithmic scale. That is important. In the same way, as far as phase angle plots are concerned, we need to draw the angle contribution of open loop transfer function. So it will be like gj omega followed by hj omega, which will be in degree, followed by frequency, which will be in logarithmic scale. That is important. So once you have done with this, now let us try to understand how or what will be the nature of the magnitude plot, or you can say the phase angle plot will be looks like. These are the examples, very general example. So this figure indicate the magnitude plot and this figure indicate the phase angle contribution. So see, on the y-axis we have indicated the magnitude of open loop transfer function, that too in your decibel. So it will be like 20 log to the base 10 of mod gg omega hg omega. And on x-axis we have taken frequency, that too on logarithmic scale, which will be in radian per second. So it will be like zero point 0.1. Then we need to multiply this by 10. You will get 1 within a span of 10. Then multiplied by 10, you will get 10, and then again multiplied by 10, you will get 100. So it will be like this. In the same way, as far as phase angle plots are concerned, on the y-axis we need to indicate the phase angle contribution, that will be in degree, followed by, on x-axis we need to take frequency. But remember one thing, whenever we try to draw Bode plot, we need to take spatial paper, that is called as semi-log paper. So this magnitude plot, or you can say phase angle plots, we have drawn on the semi-log paper. This is very important. Semi-log paper. Why it is called a semi-log paper? Because the x-axis is constituted by a logarithmic scale, whereas y-axis is a simple normal axis. That's why it is called a semi-log paper. And as I told you, that frequency we need to indicate uh, on the logarithmic scale. That's why we need to take semi-log paper. This is very important. So please take your pen paper and try to draw this rough sketch of magnitude plot followed by phase angle plot. If you have done with this, then this is called as the magnitude plot, and this is going to be the phase angle plot. Now, once you have done how to draw magnitude plot and how to draw phase angle plot for a system, then we need to calculate the gain crossover frequency indicated by symbol omega gc, followed by phase crossover frequency indicated by symbol omega pc. Now, what is gain crossover frequency? It is nothing but that complex frequency where the magnitude plot of a system is going to cross 0 dB line. This is very important. It is that value of frequency where the magnitude plot of a system is going to cut the 0 dB line. In the same way, what is phase crossover frequency. It is that particular frequency where the phase angle plot is going to cut minus 180-degree line. That frequency is called as phase crossover frequency. In the coming sections, we are going to discuss in detail about what exactly omega GC and omega PC. But for time being, let us consider that once you have drawn the magnitude plot and the phase angle plot for a system, then you need to determine the omega GC, which is called as gain crossover frequency, and omega PC, which is called as phase crossover frequency. What is gain crossover frequency? It is nothing but that complex frequency where the magnitude plot is going to cut 0 dB line. And what is phase crossover frequency? It is that frequency where the phase angle plot is going to cut minus 180-degree line. This is very important. And once you know omega GC, omega PC, then we need to calculate the gain margin and the phase margin. Remember one thing, in order to calculate gain margin, you have to calculate omega PC. And to calculate phase margin, you have to calculate omega GC. Now, how to calculate gain margin, how to calculate phase margin, that we are going to learn in the coming slides. But let us consider that once you know the knowledge of omega GC, omega PC, then we need to calculate the gain margin and phase margin. And once you know omega GC, omega PC followed by gain margin, phase margin, now we are trying to discuss how we can decide the stability of a system using Bode plot. So these are the conditions that we need to follow in order to check the stability of a system. Number one, when the value of omega PC is more than omega GC. This is the condition. That means when the value of phase crossover frequency is more than gain crossover frequency, in this case both gain margin and phase margin are going to be positive and the system is said to be stable. This is very important. This is the first condition. When the value of phase crossover frequencies is more than gain crossover frequency, automatically if you calculate gain margin, phase margin, both are going to be positive and the system is said to be stable. Second thing is that if the value of omega GC is more than omega PC, both gain margin and phase margin are going to be negative and the system is said to be unstable. And case number three, when both omega GC and omega PC are nothing but same, in this case gain margin and phase margins are going to be zero. And we can say that the system is marginally stable. This is very important. So please note down these three cases where we can have the flexibility to make a comment on system stability just by calculating the value of gain crossover frequency and phase crossover frequency. If the value of phase crossover frequency is more as compared to gain crossover frequency, that will be your case number one. Omega PC is more than omega GC. Both gain margin and phase margins are going to be positive and the system is said to be absolutely stable. If the situation is reverse, that means if the value of gain crossover frequency is more as compared to phase crossover frequency, that means omega GC is more than omega PC. Both gain margin and phase margins are going to be negative, the system is said to be unstable. And case number three, where both gain margin and phase margin if are exactly same, sorry, if gain crossover frequency and phase crossover frequencies are exactly same, gain margin and phase margins are going to be zero and the system is said to be marginally stable. This is very important. So please note down this. These are the special cases that we need to implement in order to determine the stability of a system. Okay, if we have done with this, let us try to understand the pictorial view what exactly omega GC and what exactly omega PC is, what is gain margin and what is phase margin. So if you see this figure here, I have shown two pictures simultaneously. First one is figure A. This is your figure A, and this is going to be figure B. So in figure A, the system is said to be stable. Now why it is stable? Let us try to understand that. Before that, first of all, try to understand what is gain crossover frequency. So as I told you that gain crossover frequency is nothing but that particular frequency or that particular value of omega where the magnitude plot is going to cut the 0 dB line. So this is your 0 dB line and this is your magnitude plot. So this point is nothing but your omega GC. See, this is your omega GC. In the same way, let us try to understand that what is omega PC. The omega PC is nothing but what? This figure is nothing but, or this part of figure A indicate your uh, phase angle plot. So here on y-axis we have taken the phase angle which will be in degree, and on x-axis we have taken the frequency which will be in logarithmic scale. And I told you that what is omega PC? Omega PC is nothing but that particular frequency where the phase angle plot is going to cut minus 180-degree line. So this particular point is nothing but your phase crossover frequency. Now because both the axes are nothing but same, see, this and this we have drawn on the same axis. So if you compare the magnitude of omega PC as compared to omega GC, we can make a comment that omega PC is more than omega GC. So this system is said to be stable. In the same way, see here, see, omega PC is more than omega GC, the system is said to be stable. And we also make a comment on gain margin and phase margin. Now let us try to calculate what will be the gain margin and what will be the phase margin. Now in order to calculate phase margin, now see, this is nothing but our gain crossover frequency. Gain crossover frequency is used to find out the phase margin of the system. See, we have drawn the dotted line and this is nothing but the phase margin, and it is nothing but positive. In the same way, suppose if you want to calculate gain margin, in order to calculate gain margin, we need to calculate omega PC, that we need to indicate, and then this particular margin is nothing but gain margin and it is going to be plus. So the moment we have omega PC more than omega GC, the gain margin and phase margins are nothing but positive. The system is said to be absolutely stable. This is very important. In the same way, if you try to focus on figure number B, here, see, this is nothing but your gain crossover frequency, the frequency where your magnitude plot is going to cut 0 dB line. And this is nothing but phase crossover frequency where the phase angle plot is going to cut minus 180-degree line. And from this, it is very clear that the value of omega GC is more than omega PC. So here, both the gain margin followed by phase margin both are going to be negative, and the system is said to be unstable. This is very important. Unstable. I hope this point is clear to everyone, and this is what the topology that we need to implement in order to determine the stability of a system using Bode plot technique. The thing is that we have to first calculate and draw the phase angle plot followed by magnitude plot. Then we need to draw the variation of open loop transfer functions magnitude with respect to frequency, angle contribution with respect to frequency on semi-log paper, then calculate the value of gain crossover frequency omega gc, phase crossover frequency omega pc, calculate gain margin gm, phase margin pm, and then apply that simple logic. The logic is, if the value of omega pc is more than omega gc, both phase margin and gain margin are going to be positive, the system is said to be stable. If omega gc is more than omega pc, both gain margin and phase margin are going to be negative, the system is said to be unstable. And if omega gc is exactly equals to omega pc, followed by gain margin and phase margin to be zero, the system is said to be marginally stable. This is very important. This is very, very important. Please note down this point. This is very important. As far as the Bode plot is concerned and how we can determine the stability of a system using Bode plot technique. What is the concept of gain margin? What is the concept of phase margin? How we can obtain gain crossover frequency? How we can obtain phase crossover frequency? That is important. Once we have done with this, let us try to understand what are the steps that we need to follow in order to draw a Bode plot for a system. So, steps to draw Bode plot. Step number one, obtain the open loop transfer function of a system whose Bode plot we need to draw. That means जो भी सिस्टम का आपको Bode plot ड्रॉ करना है, चाहे वो मैग्नीट्यूड कंट्रीब्यूशन हो या फिर फेज एंगल कंट्रीब्यूशन हो, सबसे पहले आपको वो पर्टिकुलर सिस्टम का ओपन लूप ट्रांसफर फंक्शन फाइंड आउट करना पड़ेगा. That means g of s into h of s. Now let us consider that we have a general representation for open loop transfer function. It will be like g of s into h of s equals to k in bracket s plus a, s plus b, s plus c, and so on, whole divided by s into s plus d, s plus e, and so on. So step number one is we need to obtain the open loop transfer function for a system whose Bode plot we need to draw. Then step number two. In step number two, we need to arrange the open loop transfer function into a standard form. Now, what exactly standard form is? We need to arrange them like this. So, we need to arrange them like 1 plus coefficient of s followed by s, like this. See, 1 plus coefficient of s followed by s, 1 plus coefficient of s followed by s. So, this will be the standard form. Same for zeros also. So, this will be your step number two. So whatever the constant which you have taken while arranging the open loop transfer function into standard form, so this will be your overall gain, which will be a combination of gain followed by the coefficients, or you can say constant coefficient corresponding to poles and corresponding to the zeros. That is important. So this will be your step number two. We need to arrange the open loop transfer function into a standard form. Please note down this. In step number one, obtain open loop transfer function. In step number two, arrange the open loop transfer function into standard form. That is important. Then the overall gain is something like this. So capital K is equals to small k followed by ABC divided by DE. So this is what a general formula for the overall gain K. It may not be possible that you always have all these terms into picture. It totally depends upon what kind of open loop transfer functions are given to us. So it will be like this. So g of s into h of s equals to overall gain k followed by standard form 1 plus s by a, 1 plus s by b, 1 plus s by c, and so on, whole divided by s followed by 1 plus s by d, s plus 1 plus s by e, and so on. Then step number 3. Step number 3 is nothing but a technique where we are trying to convert the frequencies which are represented in Laplace operator like s into their corresponding j omega. So all s we are going to replace by j omega. That's it. So this will be a step number 3. Wherever we have s, replace that s by j omega. That's it. So the open loop transfer function for the system will be like this. Once we have arranged them into standard form, now we need to replace s by j omega. So here we have 1 plus s by a. So instead of s, we have replaced them by j omega. Same for this. See, j omega. Again here we have j omega. Again here we have j omega. This is again going to be j omega. This is again going to be j omega. So this is the replacement of s by j omega. I hope this is clear to everyone. And then step number 4. In step number 4, we need to do the calculations for corner frequency. So how to calculate corner frequency? That is important. So corner frequency is simply the coefficient of j omega which is available in the standard form. We need to take inverse of that. So that will be your corner frequency. So these are the frequencies where the slope of the magnitude plot is going to change either by plus minus 20 dB per decade or plus minus 40 dB per decade. So this is what the definition for corner frequencies. So corner frequencies are nothing but those frequencies where the slope of magnitude plot of Bode plot is going to change either by plus minus 20 dB per decade or plus minus 40 dB per decade or plus minus 60 dB per decade or plus minus 80 dB per decade. It totally depends upon how many number of poles and zeros are available corresponding to that particular corner frequency. And suppose if the corner frequency is due to simple pole, then the slope of the magnitude plot is going to be minus 20 dB per decade, or it is going to change by minus 20 dB per decade. In the same way, if the corner frequency is due to complex conjugate pole, this is very important, then in that case the slope of the magnitude plot is going to change by minus 40 dB per decade. This is very important. These points you have to remember. In another case, suppose if the corner frequencies are due to simple zeros, or you can say complex zeros, then in that case the slope is going to change by plus 20 dB per decade and plus 40 dB per decade respectively. This is very important. So whenever we have corner frequency, the thing is that we need to check first that whether the corner frequencies are due to poles or zeros. If it is due to pole, it is going to change by minus 20 dB per decade. If it is due to complex conjugate pole, it is going to change by minus 40. In the same way, if the corner frequencies are due to zeros, simple zeros, then it is plus 20 dB per decade. And suppose if it is due to complex conjugate zeros, it will be due to plus 40 dB per decade. This is very important. So this is what the standard form of open loop transfer function which is available with us, where we have to calculate the corner frequencies. So in this case we have total 5 corner frequencies, out of which 3 corner frequencies are due to poles like this, and the remaining corner frequencies are due to the zeros like this. This is very important. So the corner frequencies for simple zeros are like this. So see here, this is j omega by a. So coefficient of j omega is 1 by a. So you need to take 1 by a inverse. It will be like a. So see, the corner frequency due to pole, sorry, 0 is a radian per second. In the same way, if you focus on this, the coefficient of j omega is 1 by b. So if you take inverse of 1 by b, it will be like b. So see, one corner frequency is available at b radian per second. In the same way, another one is available at c radian per second. So a, b, c are the corner frequency because of open loop zeros. In the same way, we can calculate the corner frequency corresponding to simple poles. So here we have two pole. One pole is at one pole having the coefficient of j omega is 1 by d. So you need to take inverse of that. So it will be like d. In the same way, one pole has the coefficient corresponding to 1 by e. So you need to take inverse of that. So it will be like e. So if you apply that logic, see here, this d is going to be your corner frequency corresponding to pole, followed by this e is going to be another corner frequency corresponding to e. So in this case, we have total three corner frequencies due to simple pole zeros and two corner frequencies due to simple zeros. Now we need to indicate them one by one. So first of all, we need to draw the structure. This is going to be semi-log paper, x-axis, and on x-axis we need to indicate frequency on the logarithmic scale. On y-axis we need to indicate magnitude, that will be in dB. This will be your 0.1, then 1, 10, 100, 1000, 10,000, and so on. And on y-axis we need to indicate the magnitude, that will be in dB. So 0, 10, 20, 30, and so on. So first corner frequency, that is considered that the corner frequencies due to simple zeros. Let us consider that the value of a is 0.2. So that 0.2 we need to indicate over here. So 0.2 will be like this, because it will be in between 0.1 to 1. So somewhere over here it will be like 0.2. See here, this is going to be zero point 0.1. So this point is going to be 0.2. This point is 0.3, 0.4, 0.5, and so on up to 1. In the same way, this is 1, this is 10. So this will be your 2, 3, 4, 5, so on up to 10. In the same way, if this is 10, this is say 100. So here this is going to be 20, this is going to be 30, this is going to be 40, and so on up to 100. So if you apply that logic, you can indicate all possible corner frequencies corresponding to poles, followed by corresponding to zeros. That's it. I have indicated them one by one on the semi-log paper by taking proper suitable scale. You may start the value of complex frequency corresponding to zero point 0.1, or you may start this value by 0.01, or your value may start from 0.001. That totally depends upon what will be the highest possible magnitude of corner frequency. It may be because of pole, or it may be because of zeros. So today we will stop at this particular point. Up to this point we have learned what is corner frequency and how to indicate corner frequencies on the Bode plot of a system. In the next lecture, we will continue our discussion by taking some more steps that we need to consider while drawing the magnitude plot, followed by phase angle plot for a given system, and then we will try to understand how to make a comment on system stability using Bode plot technique. Thank you.